Hi, in this video I will be going over the derivation of the small signal model transfer function of the ideal boost converter. To derive this transfer function, you have to follow the following steps. First, we will obtain the state equations for when the circuit is turned on, the MOSFET is turned on and turned off. The next is we will average those state equations to obtain a state space averaged representation, and then we will perturb the averaged equations and eliminate any second order AC terms so we can linearize those equations. We will then take the Laplace transform and finally extract the small signal transfer function. I will now start deriving the state equations for when the circuit is on and the MOSFET is essentially closed. This would yield the following equivalent circuit. So the supply would be in parallel with the inductor and the capacitor would be in parallel with the voltage load. This would be Vs, Vl, Vc and Vr, and we would start on the left hand side. So we can say that Vl is equal to Vs. We also know that the voltage across the inductor can be written as L di on dt, which is equal to Vs. Taking just the derivative term, this can also be written as Vs all over the inductance. Now for the right hand side, we can also write that Vc is equal to Vout, which is equal to Vr, and IC, the current coming from the capacitor, is equal to minus IR. Now IC can be written as the capacitance multiplied by the rate of change on the capacitance voltage, which is equal to minus V out all over R, which is also equal to Vc minus Vc all over R. And taking the capacitive term to the other side, we would yield minus Vc all over Rc. Now these are the two state equations for the time on, and the next step would be to write them in state space form. So the generalized state space form would be the derivative of x times the A matrix, the states, B and the input, and the output would be the C multiplied by the states. Now we are choosing Y to be V out in this case, and our states to be the inductor current and the capacitor voltage. The input U is equal to Vs, and to write this into state space form, that would be the derivative of IL, derivative of Vc, which is equal to the A matrix, the states that we've chosen, the B matrix, and our input U, which is Vs. So IL, Vc, we know that the derivative from this first state equation is equal to Vs on the inductance, all over the inductance, so that would be 1 all over L, 0 here. And for the second part, the derivative of the capacitor voltage is equal to minus Vc all over Rc. So minus Vc all over Rc, and the others would be equal to 0. So the A matrix here for the time on circuit is equal to 0, 0, 0, minus 1 on Rc, and the B matrix is equal to 1 all over L. As for the C matrix, as we've chosen the output to be Vout, Vout we said is equal to Vc, so the C matrix would be 0 and 1, since Vc is equal to Vout. We will now repeat the process for when the circuit is in the time off state and the MOSFET is open. So the equivalent circuit would be equal to Vs here, VL capacitor in parallel with the load. So this would be Vs, VL, Vc and Vr, and this would be Vout. To start for the state equations, we can write Vs is equal to VL plus Vout. Vs is equal to L di on dt plus Vout, and di on dt is equal to Vs on L minus Vout on L. This is the first state equation. Now we can also say, since IL, IR, and IC, IL is equal to IC plus IR. So IL is equal to C dV by dt. This is the voltage across the capacitor, plus Vout all over the R load. Now writing this on the other side to obtain the second state equation, we obtain IL all over C minus Vout on RC. So these are the two state equations, and we will now write them in state space form, where we have the same states as the time off, time on circuit. So IL Vc, the output remains unchanged, and the input is still equal to Vs. And writing this in state space form, we have the derivatives of the states, the A matrix, IL Vc, the B matrix, and Vs. So starting with the derivative of IL, we can see it's Vs on L, so the same here, 1 all over L, and the output, which we've said earlier, is the same, it's equal to Vc. So this would be 0 and minus 1 all over L. Now for the second state equation, we have IL all over C, so this would be 1 all over C minus Vout on RC, which we said Vout is equal to Vc, so that would be minus 1 on RC. Here the A matrix is equal to 0, minus 1 on C, minus 1 on L, minus 1 on RC. The B matrix is equal to 1 on L, and the C matrix, since we've chosen y equals to Vout, is the same as the other circuit. So y is equal to the 0, 1, IL, and Vc. Now for the next part, since we've obtained the state space form for the time off and time on circuits, the next part would be to average the state matrices and then apply perturbation to obtain the small signal transfer function. So for the state space averaging, we will write the state space equations for the time on circuit. We will denote them as A1, B1, and C1. And for the time off circuit, we will denote them as A2, B2, and C2. We can also say that A1 and A2 are not equal to each other, B1 and B2 are equal, and C1 and C2 are also equal. Now we can also denote the duty cycle as d for the time on, and 1 minus d for the time off. Now we can write the average state space equations as x on t, the duty cycle multiplied by A1 matrix, 1 minus d multiplied by the A2 matrix, the state x, and the same for the input. The duty cycle, B1 matrix, 1 minus the duty cycle, B2 matrix, and the input, which is Vs. The same for the output, dt times C1 matrix plus 1 minus the C2, and the states x. Now what we have here essentially is an approximation of the switching converter as a continuous linear system, and the duty cycle that we've introduced here and here for the time on and time off is essentially a weighting factor to combine the state equations into a single average state space equation. The last step now would be to perturb the system and extract the transfer function. So in this step we will apply the system with a perturbation. This is where the signals are split into their DC and AC components. So here we would write the states xt as a DC component plus an AC component, which we will call x hat, and we will apply this to all the states. So the same with V out, a steady state DC component, and V out hat, and the same with the duty cycle, D plus D hat. As for the input Vs, we will assume that there is no perturbation, so the input will be a clean, for example, 12 volts. There will be no AC components. This will simplify the extraction for the transfer function in the Laplace domain. So we will assume that Vs hat is equal to 0 for this case. With Vs hat equal to 0, we will then obtain a transfer function between the voltage output hat and the duty cycle. So this is the small signal transfer function of the ideal boost converter. Now that we introduced small AC perturbations, the next step is to substitute these new signals into the average state space equation. So for substitution, we will now write the average state space equations as follows. So we have the derivative being the DC term and the small signal AC perturbation, and we will begin to substitute the duty cycle as follows. One minus D plus D hat A2, which is equal to X plus X hat, and for the input plus D plus D hat b1 plus 1 minus d plus d hat multiplied by b2 vs. And for the output, since y is equal to v out, we would write v out plus v out hat, which is equal to d plus d hat multiplied by c1 plus 1 minus d plus d hat multiplied by c2 and these states. So what we've done here is we've substituted these new states, including their DC and AC terms, and we've substituted them inside the averaged state space equation, and we've obtained this state space equation over here, where the capital letters for the signals, for example D, denotes a DC, and the signals with the hat denote the AC terms, and the same here for the states and for the output. Now we know that the derivative of x plus the AC term of x with the t can be written as the derivative of x hat by the t, because the derivative of a DC term is always equal to 0. If you expand these two equations and you group the terms together, we can write this equation as follows, where we have d x hat t is equal to the DC terms, which is equal to a x plus b vs, equal to the first order AC terms, which is equal to a x hat t plus a1 minus a2 times the DC state x plus b1 minus b2 multiplied by vs, and the AC term of the duty cycle, and the second order AC terms, which is equal to a1 minus a2 multiplied by x hat and d hat. So this is equal to the steady state DC term. This over here is equal to the first order AC terms, because you have an AC term x over here and the duty cycle here, and this is equal to the second order, because you have two AC terms multiplied with each other here. And for the output, we have V out plus V out hat, which is equal to the DC term C multiplied by X, and the AC term C X hat plus C1 minus C2 multiplied by X, and the AC term of the duty cycle. One thing I forgot to add is that the A, B, and C matrices over here, here, and here are equal to A1 D plus A2 1 minus D. Same goes for B, B1 D due to cycle, B2 1 minus D, and C, C1 D plus C2 1 minus D. Now if we neglect the second order terms and linearize the state space equation, we can write the steady state values, steady state, as follows. So the steady state would be equal to 0 because the states would not be changing and the system is at equilibrium, and that would be equal to AX plus B Vs, and the output Vout would be equal to Cx. And if we separate the AC first order AC terms, our AC model can be written as the x hat is equal to A x hat plus A1 minus A2 x plus B1 minus B2 Vs and D hat, and the output Vout, the AC output, is equal to C x hat plus C1 minus C2 x and D hat. So this is the AC model and this is the steady state model, and here we have eliminated and neglected the second order terms, and we have effectively linearized our system. Now the last step would be to extract the transfer function in the Laplace domain. Now to extract the transfer function, we will take extract transfer function. We will start by taking the Laplace transform of the state space form, so that would be equal to S x hat the S domain A x hat S plus A1 minus A2 x plus B1 minus B2 Vs and D due to cycle in the S domain, and Vout in the S domain is equal to C x hat S plus C1 minus C2 x and ds. Now if we group for x and substitute in Vout, we obtain, after grouping, we obtain the following. So x can be written as x hat S, which is equal to S, the identity matrix minus A, and the inverse, multiplied by A1 minus A2 multiplied by X plus B1 minus B2 Vs and multiplied by ds. substituting this in V out, we would get V out hat is equal to C multiplied by S identity A minus 1 A1 minus A2 multiplied by X Vs the duty cycle and plus C1 minus C2 multiplied by X and multiplied by the duty cycle. So now what we can do is we can take the duty cycle over here and over here and divide this side of the equation and this side by ds hat to obtain v out hat all over the duty cycle hat s, and this will give us the small signal transfer function. To simplify even further, we said earlier that A1 is not equal to A2, B1 is equal to B2, and C1 is equal to C2. So this term cancels out and this term cancels out, and the small signal transfer function can be written as follows. V out hat all over ds hat is equal to C S identity matrix minus A the inverse multiplied by A1 minus A2 multiplied by X. And if we solve this, we obtain the transfer function in the Laplace domain. So what we're going to do now is I'm going to solve this equation quickly. So we can write V out all over the duty cycle is equal to the C matrix 0 and 1 with S multiplied by the identity matrix S 0 0 and S minus A which is equal to A1 multiplied by the duty cycle D all over RC plus A2 which is multiplied by 1 minus the duty cycle, so that's 1 minus D all over L, 1 minus D all over C, and minus 1 minus D all over RC. Now we take the inverse of this entire matrix and we multiply by the steady state values of X. So X in this case is equal to the steady state of IL and the steady state of V out. So in that case we would have A1 minus A2 which is equal to 0 1 on over L minus 1 all over C 0 and the steady state states IL and V out. So now if we add this entire matrix over here, we are left with the following. So that would be V out hat over D hat 0 and 1 S minus 1 minus D all over C, 1 minus D all over L, and S plus 1 all over RC. Take the inverse of that, and on the right hand side we have the 0, 1 minus C, 1 all over L, 0, IL, and V out. Now if we take the inverse and multiply with the C matrix, we end up with V out so that would be 1 all over S plus 1 on RC plus 1 minus D squared all over LC multiplied by the matrix 1 minus D all over C S, and multiplied by 0, 1 on C, 1 all over L, 0, and the steady states IL and V out. We're almost done here, so we just need to now multiply these three matrices with each other, and that way we obtain the Laplace transfer function. So now we can write, after multiplication, V out all over S in the is equal to V out 1 minus D all over LC minus ILS all over C multiplied by 1 S plus 1 on RC plus 1 minus D squared all over LC, which can be further simplified to V out all over S duty cycle V out 1 minus D IL LS S squared LC plus SL all over R plus 1 minus D. So this right here is the small signal transfer function in the Laplace domain. It is quite a long derivation, but you always start from the state equations for the time on, time off. You take the state space average, you insert the perturbations, and then you extract the transfer function. Now V out over here is the steady state, and IL is also the steady state values. You can also write this transfer function in terms of V out. So for a boost converter, we know that IL is equal to V out all over 1 minus D R. If we substitute this into this transfer function, we can rewrite this transfer function as follows. So after substitution, the transfer function can be written in its final form as V out over D is equal to V out 1 minus D multiplied by R 1 minus D squared minus SL S squared RLC plus SL plus R 1 minus D squared. Thank you for watching. In the next video I'll be deriving the transfer function for the non-ideal boost converter. This will include the parasitic resistance in the inductor. This will provide us with a better approximation of the transfer function of the non-ideal boost converter.